Hi, Michal. Welcome to LUIS. It's a pleasure to have you here.
Hi, Matteo.
So I'm just going to ask you some questions about you and your work. Let's start a bit with your CV. So you arrived in Berkeley around the turn of the millennium, and that was the time when algorithmic game theory was being born. There were some fantastic people on the faculty there. So did you immediately perceive the novelty of the approach? How did it go?
Yeah, so I'm very thankful for being at Berkeley exactly at that time when algorithmic game theory came into being. It was really the formative years of AGT, algorithmic game theory, and there was this sense of a big intellectual frontier coming up. As you said, great people were there. Christos Papadimitriou was there at the time. My advisor, John Chuang, and Scott Shenker, Ion Stoikai worked with all these people. Also, Tim Roughgarden was there as a postdoc. In the early days, back then, it was not nearly as clear or well-defined as it is now. So it was this sense of merging these two disciplines that progressed on parallel lines until that time, economics and computer science. And because of the internet, as a huge computational platform, and it was clear that it's going to change the world, and markets are going to be run on this huge computational platform, there was this sense that these fields should get together, and that's what algorithmic game theory was all about.
I see. So there's a number of important computer science contributions to the game theory literature. So I'm thinking algorithmic mechanism design, characterizing the inefficiency of equilibria through the price of anarchy, and so on. So are there some of these questions? Which ones are the ones that attracted you to the field to start with? And how did you approach the field at the start?
That's a great question. And actually, for me, in the beginning of my PhD, I looked at incentives for cooperation in peer-to-peer systems. So I don't know if you recall, but that was the time that Napster came up, and there were all these file sharing systems, and we had to design incentives to incentivize people to share their resources and not only consume. And game theory happened to be a great tool for designing these incentives. Then I started to look at algorithmic mechanism design, which was also huge. And I have a funny story from my Berkeley days. So apparently, even before I knew what mechanism design is all about, I happened to design a mechanism which was probably the most influential mechanism I ever designed. I can tell you about it. So that was in my very early days, even before I started my PhD at Berkeley. And I had to commute from Berkeley to San Francisco, to the city. And there was this thing for commuters at the North Berkeley BART station. Drivers would come in a line, and riders would also stand in a line. And then drivers would pick up riders in order to take the carpool lane to save traffic. So it was a very simple mechanism, one rule. So one line of drivers, one line of passengers. They would fill up, pick up at the North Berkeley BART station, drop off at the Embarcadero, which was the first city exit. But here's the thing, many people had to arrive at Civic Center in the city, which is the third or fourth exit, but everybody would drop off at the Embarcadero Center, and then some drivers who would want to save all the traffic inside the city would want to go all the way to Civic Center, but they would need to drop off people. Heavy traffic, lots of time, and the same for many passengers, and the same for me. I had to go to Civic Center. So after a few frustrating commutes, I did the following. One morning, I came up with a sign saying Civic Center. And I held with the sign, and I got very disapproving looks at me. And one person even told me, noticing that I'm not from the US, that's not how we do things in this country. But a few minutes later, a driver happily picked me up, going all the way to Civic Center. And then apparently, very quickly, two lines were formed, and that was every morning, one line for Embarcadero Center, one line for Civic Center, and that's how things, and that really improved social welfare. It improved everybody's welfare. That was a very simple mechanism before I knew anything about fancy analysis, just one sign and a small incentive tweak to make everybody better off. And what was really, really nice is that 10 years later, when I visited Berkeley, I saw these two lines still there, Embarcadero Center and Civic Center.
That's some very good applied motivation to get,
Yes.
to get into the field.
Yes.
Okay, so if you had to, say, mention one contribution of computer science to game theory, one important paper that you particularly like, what would you say?
That's a very hard question because there are so many great contributions of computer science to game theory. I guess what I consider the big bang of algorithmic game theory was the first paper of Nissan and Ronen, Algorithmic Mechanism Design, which really created this new agenda of doing mechanisms in a computationally feasible way. But actually, maybe the one chapter that I really like the most is Noam Nissan's chapter on, I think it's called Algorithmic Mechanism Design through the lens of multi-unit auctions. And what I like about this chapter is that it grounds the discussion around a deceptively simple setting, which is a market with identical items. All items are identical. And yet, it very nicely captures the richness of this area, the tension between incentive constraints and algorithmic constraints. And somehow, this very seemingly simple setting has it all. It has the computational complexity questions and communication complexity question and the lens of approximation, which is significantly important, like the way we computer scientists view the world through this lens of approximation. We are willing to compromise on optimality in order to achieve some other goals, like computational feasibility or simplicity or robustness. And we have this lens of approximation that lets us do it in a rigorous way, in a mathematically rigorous way. So we are willing to compromise, but not too much. And that paper somehow had it all in a very clean, elegant, mathematically deep sense.
That's great. So zooming out a little bit, so there's a number of interesting, important questions that have been tackled by computer scientists in the last 25 years. I'm thinking about secretary problems and profit inequalities, which also have been important questions for applied mathematicians in the last part of the last century. So some would say that these questions have been rediscovered by computer scientists. So what would you say is the novelty of the approach of computer scientists and why is it being so successful?
Profit inequality is a great example. Profit inequality is a beautiful setting. So it's about a gambler who is facing some, boxes with prizes. It's part of this great literature on optimal stopping theory, where the gambler needs to decide when he's being presented prizes, and at each point, the gambler has to say, do I take this prize and go home and stop, or do I continue, in which case I forego that prize forever? And there was, as you said, in the late 70s of the previous century, great papers on this profit inequality by statisticians and mathematicians. And then computer scientists took this topic. And what the novelty that they brought was in several aspects. So first of all, we love combinatorics. We love combinatorial structure, and we have the language and the tools to deal with combinatorial structure. So rather than, say, looking at a single selection problem, we now extended this profit inequality literature into combinatorial settings, matching markets, combinatorial auctions, and we were able to generalize this beautiful result of a very simple threshold algorithm that gives the gambler some guarantee into all these much, much more complex combinatorial settings. So that's one thing. Another thing is that we love applications. So we looked at all these beautiful applications of even the simplest profit inequality into the design of simple auctions, for example. So we were able to grab that result and design approximately optimal, simple auctions for settings that we did not know how to handle before. Another thing is we came up with different variants and different benchmarks. Data-driven and learning approach is huge in computer science. So rather than assuming that the underlying distribution of these prices are all well known, maybe we only have sample access to these distributions. So we have this notion of sample complexity. How many samples do you need to have? What's enough information, enough number of samples that you need in order to get these results? So it's about the different information structures and the different variants and learning approach and combinatorics and applications that really, that computer scientists brought into this literature. And I think this is just one example of how we look at one example that was known before, but we extend it in ways that are meaningful for us.
So now moving to the very near present. So you're here at LUISS to talk about a recent project on contract design, which comes from collaboration with economists and is published in a great economics journal. So what was it like to work with economists so close by, and tell us more about this collaboration?
Contract design is, so first of all, let me say a few words about algorithmic contract design. So for many years, algorithmic mechanism design was a huge topic in algorithmic game theory, and it's about how to create incentives for agents to reveal their private information truthfully. And we've been playing in this playground for like 25 years. Great literature. But then there is a huge aspect of incentives that was overlooked by computer scientists, mostly overlooked, which is about incentivizing effort, incentivizing desirable behavior and actions by the agents. And that's what the economic literature of contract design is all about, how a principal can incentivize an agent to exert the desired amount of effort into a task. And now that many of these markets for incentivizing effort are happening again in the internet, in these huge computational platforms for freelancing and outsourcing, and even online courses, which is all about incentivizing students to exert effort in a meaningful way into learning. So all these huge markets are taking place in a computational platform. The algorithmic lens is again very crucial and meaningful, and we have to examine and explore this setting from a computational algorithmic perspective, again through the lens of, say, approximation, combinatorics, and that. So in fact, for me, this topic is very close to my heart because my very first collaboration with Noam Nissan, who was my postdoc supervisor when I came back to Israel after my PhD at Berkeley, was about algorithmic contract design. That was, I came from Berkeley, I took this class in the economics department there about the principal agent model, and I thought about applying it to multi-hop routing at the time, and then I came back to Israel and we started to think about, together with Noam Nissan and Moshe Babayov, about a combinatorial setting. How do you incentivize a team of agents where the team has an interesting and rich combinatorial structure where people might substitute each other, complement each other? And that was this one paper back in 2006, I believe. And then only recently, in the last 5 years, with the help of many brilliant minds like Tim Roughgarden and Paul Dutting and Inbal Talgam-Cohen, who also was my postdoc, we started to really extend this literature. And we are looking into combinatorial structures and into simplicity versus optimality. All these aspects coming from computer science, we are applying it to the contract design lens. Now, about this paper that you mentioned, so that was a paper about ambiguous contracts. So we said the very simple observation was that we have this literature on contract design, which assumes that everything is well known and the contracts are precisely defined. But then we noticed that many contracts in practice, in real life, are quite ambiguous. Like, for example, In universities, we tell our junior faculty, if you do well, you will get promoted. But what does it really mean to do well? Or insurance companies say that they will, compensate good drivers. What are good drivers? It's all very ambiguous. And we came up with a model that models ambiguity of contracts in a mathematically precise way. And we asked the question, what can the principal who designs the contract benefit from deliberately infusing ambiguity into the contract? That was the motivation behind that paper. And we were able to model it and explore this and answer a large amount of questions about this model. In what types of contracts? There are many different classes of contracts. So in what classes of contracts can the principal benefit from this ambiguity? We wanted to quantify, which is a thing that we always do in computer science. We want to quantify. If it's not optimal, then how much? So we wanted to quantify how much the principal can benefit from ambiguity. And we had all these questions coming from the algorithmic computational lens that we are used to look at problems through about these ambiguous contracts. And then, so that was originally with Paul Duding and Daniel Peretz, who was my master's students back then. And then in EC, in our main conference of the field, Economics and Computation, Larry Samuelson was there. I believe he was one of the PC chairs back then. And we had a great chat with him. He's brilliant. It was an amazing conversation about ambiguous contracts. And then he joined us, and we had many follow-up conversations, and then we turned this original paper into an economics paper. We added many results, different perspectives coming from Larry. It was a really great experience for me. It was really nice to see how the different perspectives can really get together in a unified way. And it was also a very good experience for me to see what goes into a good economics paper, what makes a good economics paper that gets into econometrica. So that was a great experience for me.
So since you mentioned econometrica and EC, let me just finish up with one meta question about the different fields. So different areas disseminate the research in different ways. So for example, economists and mathematicians tend to focus more on journals, and computer scientists, on the other hand, are really fond of conferences and conference proceedings. So do you see a tension between these two approaches, and how are the two fields, now that the two fields interact more, do you see also an evolution in the way that research is disseminated in these two fields?
Yes, so indeed, in computer science, we have this, very fast culture of publications. We have conference proceedings, we have deadlines, we work with deadlines. Before the deadline, we finish all the details of the papers. And so that means that we have, the pace is faster. The work, I must admit, is less polished and complete by the time of submission to a conference. On the other hand, there is this culture of economists and mathematicians who work mainly with journal papers. It takes longer. They put a lot of effort into polishing up to the last character. And the way I see it, so I think rather than viewing it as a tension, I think what we do in our community, in the what's called economics and computation community, because it's very, very crucial for us to really get all these brilliant minds together from computer science and math and game theory and economics and operations research into this conference for conversations and interaction and cross-fertilization. So we are working around these obstacles. For example, an economist might be concerned about submitting their work to EC because if it's published in a conference proceeding, which does not count towards their promotion because it's a conference proceeding, they might not be able, like good econ journals might not consider it even for publication. So the way we go around this obstacle is we allow in EC, so people send their paper, their full papers, they're being reviewed. If the paper is accepted, then we allow to publish it in the proceeding as a one-page abstract. And that's one way of handling. Another tool that we have in recent years is a forward to journal program, where papers that are already accepted to EC can be forwarded to journals, different disciplines, including economics, where the reviews from EC can be transferred to the economics journal, which can expedite things there. So we are working around these things because the most important thing for us as a community is to have a cohesive community with all these different aspects, perspectives, and disciplines.
Thank you very much, Michal. This was great talking to you, and I hope you enjoy your time at LOUIS today, and hope to see you soon around.